So anyway, things that look like that. It's called an equation, and it's characterized by that symbol right there, which is what? The equal sign, yes. What does that equal sign mean? Perfect. It's kind of tough to define it without using the word equals, isn't it? Yeah, what's on each side, what's on one side has exactly the same value as what's on the other side. In fact, one way we can think about it is as a balanced scale. What's on one side exactly balances what's on the other side. Now, all equations start out in this form, like this, as a variable equals a number, or a number equals a variable. They're built up from there. If I want to build that up, I can use any of my basic operations. Now, we've seen addition, subtraction, multiplication, division, powers, and roots. We're going to stick to the first four, the big four. Let's say I want to build onto this with addition. Let's say I'm going to add 7. Well, I add 7 here, now I have x plus 7. However, if I add 7 to that one side, the scale is going to tip unless I do what? I have to do the exact same thing to the other side. I add 7 on the other side. What's 4 plus 7? 11. X plus 7 equals 11 is just this original equation, but I built onto it by adding 7 to both sides. Well, for the most part, we're not going to be arbitrarily building equations like that. The command that we're going to be given is going to be to solve an equation. What we're really being asked to do when we're asked to solve an equation is we're being asked to take it apart. So to take it apart, we look at this was built by adding 7. How do we remove that? We subtract 7. That removes that piece. Now again, if we subtract 7 to from one side, that scale is going to tip unless we do what? Subtract it from the other side. Let's do exactly the same thing to both sides. 11 minus 7 is 4. So we have taken it apart and we got it back to that form of a variable equals a number. And when we're asked to solve, that's all we're being asked to do is to take it apart and get it back to that original form of a variable equals a number. Now this equation, we built it. So we knew it was built by adding 7. So we knew how to take it apart. The trick is looking at the equation and figuring out how it was built so that we know how to take it apart. We might have something like 8 equals y minus 3. To figure out how it was built, we locate the equal sign, then we locate the side of the equal sign that has the variable on it. In this case, it's that right side where it's y minus 3. And then we have to ask ourselves a couple of questions. One of them is, what is keeping y from being by itself over here? The 3 is, yes. And of course, the way it was built onto the y, or the way it was attached to the y, like you said, is subtracted. So this equation was built, what was done to the variable, in this case y, it was built by subtracting 3. So how am I going to take it apart? I'm going to add 3. Very good. So I add 3 to remove that, leaves me with y, and you're absolutely correct. I have to do it to both sides or my scale is going to tip. 8 plus 3 is 11. So 11 equals y, or y equals 11. If we're not sure of ourselves, we can always double check it by putting 11 into the equation to replace y. So instead of y minus 3, it's 11 minus 3. And we use our order of operations to combine anything that we can. 11 minus 3 is 8. So we do have exactly the same value on both sides of the equation. Well, those first couple are pretty boring. Most of the time, we're going to work with equations that look something like this. 3x minus 7 equals 41. So again, we have to figure out how it was built. Fine, there's the equal sign. This is the side of the variable. Now in this case, there's a couple of things keeping our variable, in this case it's x, from being by itself. 3 and the 7. What operation was used to attach the 3? Multiplication. How about the 7? Subtraction. So now we have to look at what order those were built on. X has been multiplied and it's had something subtracted from it. Order of operation says which one happened first. Do we multiply first or do we subtract first when we order of operations? We multiply. So when this equation was built, the first thing that was done to x is it was multiplied by 3. And then 7 was subtracted from it. Now remember, when we solve an equation, we're trying to take it back apart. So when we take something apart, imagine putting together a piece of furniture that you've bought, or maybe putting together a toy for one of your kids. You've just finished putting it together. You've just put on that last piece. If you need to take it apart for some reason, what's going to be the first piece you take off? The last piece you put on. And it's the same way for an equation. The last piece that was put on is the first piece we take off. That subtracting 7 is the last piece that was built on. So that's where we start to take it apart. How do we take that off? We add 7. That removes that piece. Leaves us with 3x there. Of course, we got to keep that scale balanced, the equation balanced. We add 7 to the other side. 41 plus 7 is 48. Perfect. Now we've got to get rid of the multiply by 3. We do that by divide by 3. Good. That 3 is gone. We're left with x. 48 divided by 3 is 16. Now again, we can double check by putting that back into the original equation where the x is. Instead of 3x, we use 3 times 16. Minus 7 equals 41. Well, the right side's already just a single number. So now we're going to reduce the left side. 3 times 16 is 48. And minus 7 is 41. So we have the same value on both sides. We might have something like this. So again, there's our equal sign. The left side here is where our variable is. We've got a few things keeping x from being alone here. We've got the times 2, we've got the squared, we've got the plus 9. Which one happened first? What was the first thing that was done to our variable? The exponent, squared, right? What would happen next? Multiplied by the 2, good. And then finally, add the 9. 9 was added to it. So we're going to take it apart. What's the first piece we take off? Add 9. We do that by subtracting 9. Again, we do it from both sides. That's just removing the piece here on the left. We got 2x squared. 41 minus 9? 32. What's the next piece we remove? So we remove the multiplication, so we divide by 2. Good. Again, we do it to both sides. Oops, my 3 left me there. There we go. So dividing by 2 on the left just removes that 2. We have x squared. What's 32 divided by 2? 16. Good. The last thing to remove is the squared. How do we remove that? Perfect. Square root. The square and square root cancel out. We have x. The square root of 16 is 4 or negative 4. Negative 4 squared could also be 16. So when we have equations like this where we have to use a square root to solve it, we sometimes have more than one solution that we have to worry about. Later on in the course, we'll talk about quadratic equations. Quadratic equations are equations that have squared in them like that, x squared, and they typically have 2 solutions. Now, as always, we could replace x in this equation with that solution and see if it worked. Is 2 times 4 squared plus 9, does that actually give us 41? Well, that would be 2 times 16. 2 times 16 would be 32. Plus 9 is 41. So we get the same value on each side. So we know the 4 works. Let's test the negative 4. Well, if that were a negative 4, what's negative 4 squared? 16. So we end up 2 times 16 is 32, plus 9 is 41. So it does work. Both of those, positive 4 and negative 4, are valid solutions to that equation. We may run into things like this. We look at this, we find our equal sign right there. We identify where our variable is on the left side, but it appears twice. The x is there twice. We can only solve these equations if there's only one variable and if it appears only once. So we have to figure out some way to get this down where the variable appears only once. There you go. In this case, if we go back to thinking of that idea of a balanced scale, the 5x and the 2x are on the same side of the scale. So you're exactly right. We can just push them together in one big pile or combine like terms. 5x and 2x make 7x. And we have, this equation has not changed. It doesn't affect the balance of this at all. And now this looks just like the last couple of examples we've done. We can solve it by doing what? Subtract 4. 7x equals 49. And then divide by 7. X equals 7. Again, you could go back and replace the x's with 7s to make sure that the answer double checks. I'm going to assume you guys can do that. Did you have a question, Dakota, or are we just getting some static from you? Okay. How is this one different from this one? The big difference is perfect. Yeah, we find the equal sign, it's right there. When we look at the variable, it appears twice again, but 5x is on one side and 2x is on the other side. We can't just push them together to make one big pile anymore because they're not together on the scale. So somebody said you got to subtract 2x. That's exactly right. We have to get rid of one of them. And the mechanism we use to get rid of something, if we want it to be 0, we have to use an additive inverse. If you remember our rules or properties of numbers from last week, additive inverse will give us 0. First, we got to choose which one we're going to get rid of, the 5x or the 2x. We typically will try, it's easier if we get rid of the smaller one. In this case, that is the 2x. It's a positive 2x. So if we subtract 2x, negative 2x is its additive inverse. That'll give us 0 there, or cancel that out. So we're left with 52 on that right side. We subtracted 2x from the right side. We have to make sure we do what to the left side? Subtract 2x. Now when we add or subtract, we can only combine things with the same name. So the only place we can subtract 2x from is 5x. 5x minus 2x is 3x. So we've got 3x. We still have the positive 4 or plus 4. So 3x plus 4 equals 52. Again, this looks just like some of the equations we've solved before. Where do we start? What do we do next? Subtract 4. So 3x equals 48. And then divide by 3. Perfect. X equals 16. So these two equations demonstrated the two steps that sometimes have to be taken before we can solve an equation. Step 1 is to combine on each side of the equation. So wherever the equal sign is, if we combine stuff on each side, we combine it. The second thing we have to do, the second step we have to take, is make sure that they're down to the variable appearing just once. That's like in this one over here on the right side. There was nothing we could combine, but the variable appeared on both sides. On the left side, after we combined 5x and 2x, the variable only did appear once at that point. We didn't have anything more to do. The third step then in solving and dealing with equations is to solve. And resolve just means to take apart. Get it back to that form where it's a variable equals a number. Now, of course, we can run into other things. Here, of course, what jumps out at us is parentheses. Whenever we see parentheses, similar to order of operations, it should scream at us, do something here first. So 3x minus 4 is in the parentheses. Can we combine anything inside the parentheses? No. So when we see parentheses, there's always two things to check for. That's one of them. That's the first thing to check for, is there anything to do inside these parentheses? Here that answer is no. The second thing is there anything that needs to be done to the parentheses? In this case, that parentheses is being multiplied by 5. If you recall the way we deal with that, the shortcut is to distribute. 5 times 3x is 15x. This is 5 times the negative 4 is negative 20, and that still equals 40. What do we do next to solve? Add 20. So we're left with 15x on the left side equals 60. And then we divide by 15. X equals 4. Well, these can get more difficult than that. We can run into something like this, just a little bit more complex. Well, when we look at this, we see that there are things that can be combined on each side. So we can go each side at a time. I'm going to do the left side here first. On the left side, we see parentheses. Anything to do inside those parentheses? No. So what do we have to do next? Multiply by the 7. 7 times 5x. 35x. 7 times negative 1. Negative 7. Now we still have that negative 3 there. We are not done on the left side. There's more that we can combine, so let's stay there. What can we combine on the left side? Negative 7 and negative 3. So the 35x doesn't change. Negative 7 and negative 3 makes negative 10. Over to the right side. Parentheses. Once again, there's nothing to do inside those parentheses. So we're going to move out to multiplying by the 3. 3 times 3x makes 9x. 3 times 9 makes 27. And of course, we still have that positive 15 on the end. Again, we can combine stuff yet. We can combine 25 and 15. So we still got 9x plus, should be 27, thank you. So 27 plus 15 makes 42, good. So what we've done so far is that first step. Combine on each side of the equal sign. Now the second step, does the variable appear only once yet? No, it's on both sides yet, so we still have to take care of that. How are we going to take care of that? Perfect. 9x is the smaller one, so we're going to subtract 9x. Subtracting it over here, 35x minus 9x is 26x minus 10 equals 4. Then what? That's not 4, that's 42. My 2 disappeared on me, sorry. 42, there we go. Now what? We add 10. So add 10, 26x equals 52. And we divide by 26. Good. X equals 2. Now, they can get quite a bit uglier than that. We can get more parentheses and stuff like that in there. Let's do an example. So 5 times, in parentheses, 2x plus 3, minus 3 times, in parentheses, 3x plus 7, minus 4 equals 2 times 4x plus 11 minus 7 times x minus 8 plus 1. Now again, this looks like a beast, but we just go step by step. Here's our equal sign. Let's start on the left side. What can we do first on the left side? Well, we go left to right. This parentheses, there's nothing to do inside it, so we're going to, well, just perfect. Distribute the 5. 5 times 2x, 10x, 5 times 3, 15. The next parentheses, nothing to do inside it again, so we're going to multiply by not 3, but negative 3. Negative 3 times 3x, negative 9x, negative 3 times 7, negative 21. We still got the minus 4 there, negative 4. So on the left side, we can still combine 10x and negative 9x make 1x or just x. 15, negative 21, and negative 4 make negative 10. Perfect. Minus 10. Now we've combined everything we can on the left side. Let's go to the right side. Same type of thing over there, the first parentheses. Anything to do inside the parentheses? No, so we will multiply by the 2. 2 times 4x, 8x. 2 times 11, 22. Next parentheses is times negative 7. Negative 7 times x, negative 7x. Negative 7 times negative 8, positive 56. We have the positive 1 out there. Once again, we can combine 8x and negative 7x make 1x or just x. 22, 56, and 1 make 79. We've combined on each side. Our next step is to make sure the variable appears only once. Right now, there's an x on both sides. So I'm going to get rid of it. I'm going to subtract an x. Well, something went wrong here, didn't it? What happened to our variable? It disappeared on both sides. We tried to take it off of one side, and it went away on both sides. We're left with the statement here of negative 10 equals 79. This is what is called an indeterminate equation. An indeterminate equation means you can't determine an answer. The simpler way of saying it is there's no solution here. Is there any number I could put in here for x that would make negative 10 equal to 79? No, it's not possible. Since these numbers are different, this can never be true, so there is no solution. No value of x that'll ever make that true. Now the other side of that might look like this. I'm going to come back and fill in a piece there yet. Okay, so what do I have here? Let's look at this. Tell me what to do. Okay, so we multiply by the 2, we get what? 10x minus 6. Good. What's next? So negative 3, we distribute that, we get minus 6x minus 12. Good. Of course, we have the plus 20. What's next on the left side? Combine like terms, we're going to get 4x and, careful, 2. There we go. Negative 6 and negative 12 make negative 18 plus 20 is 2. Perfect. On the right side, where do we start? Times 3, good. We distribute the 3, we get? Perfect, 12x plus 3. And then? Perfect, we distribute the negative 2 to get? Negative 8x plus 10, good. And we got the minus 11, of course. So then what do we do? Perfect, we combine like terms, 12x and negative 8x make 4x. 3, 10, and 11 make positive 2. Well, there's still a variable on each side, so we're going to get rid of one by subtracting 4x. Unfortunately, once again, both of them disappeared. We have 2 equals 2. Is that true? Is there any number I can put in up here for x that would make that not be true? No, no matter what x is, 2 will always equal 2, won't it? That's saying there's infinitely many solutions. In other words, any number can be put in there for x in that equation, and it'll work. No matter what value you put in for x, that equation is true. This is referred to as an identity. 2 equals 2 no matter what x is. Let's have a little fun. Yeah, let's not quite that much fun yet. Even I have a heart, sort of. Let's look at something like this. Of course, we have that fraction bar. And when we talked about order of operations, we said that it was also an enclosing symbol, which said we had to do everything on top first. So when this equation was built, x was multiplied by 2, or sorry, not by 2, multiplied by 5. Perfect. X was multiplied by 5, and then 2 was subtracted. Once everything was done on the top, then we could divide by the 3. That fraction bar says you have to do everything on top first, then, of course, you would do everything on bottom. There's nothing to do here. Then you can divide. So dividing by 3 is the last thing that happened. So when we go to take it apart, what's the first piece we take off? Yeah, the dividing by 3. So we're going to multiply by 3. We multiply by 3, it just removes that 3, giving us 5x minus 2. We multiply by 3 on the other side is 33. Perfect. Then what? We add 2. Good. 5x equals 35. And then we divide by 5. Perfect. X equals 7. Okay, now we'll take that next step. What do we do first here? Exactly like the one we just did. What do we do first here? Multiply by 3 to get rid of that. Down here, we're going to multiply by 2 1/4 to get rid of that. So over on the left side, we just have the 2/3 x minus 1/2. On the right side, we've got to multiply that out. Now, I don't have a fraction calculator on screen here, so I'm going to multiply it out by hand. Many of your scientific calculators have fraction functions. You are welcome to use those. So I get 63 over 8, or 7 7/8. Any questions where I got the 7 7/8 from? That's just 3 1/2 times 2 1/4. Do you guys know how to use the fraction keys on your calculator? Most of your calculators, if you got the Texas Instrument, you have an ABC key. Casio is usually the same. Casio Sharp either has that key or it has something that looks like this. It's a fraction button. If you have the ABC key, it's pretty straightforward. You would just enter 3, press the ABC key, 1, press the ABC key, and 2. That enters 3 1/2. Then you press the multiplication, the times key, 2, ABC1, ABC4, that's the 2 1/4. If you hit equals, it'll spit out something that looks like this, which is 7 7/8. Now what do we have to do over here? Add 1/2. So we got 2/3 x equals 8 3/8. That's just 7 7/8 plus 1/2. Then what do we have to do? Yeah. Technically, we're dividing by 2/3. But when we divide by 2/3, we multiply by the reciprocal. 8 3/8 divided by 2/3. Instead of dividing by 2/3, we're going to multiply by the reciprocal, which is 3 over 2. And we're going to change this into an improper fraction. 8 times 8 is 64, plus 3 is 67 over 8. 67 times 3 is 201. 8 times 2 is 16. And then, of course, we have to reduce that back down. So we go from an improper fraction, like 201 over 16, back to a mixed number. It's a division and remainder. 16 does not go into 2, so we leave a blank above the 2. 16 goes into 20 once. That's 16. We subtract. 20 minus 16 is 4. Bring down the 1. 16 goes into 41 twice. 2 times 16 is 32. That's 9 left over. We're at the end of the number, so that's 12 and 9/16. The fraction calculator is a huge help here if you have one. I trust at this point that all of you can do the operations with fractions if you needed to. It's just a matter of time using the fraction calculator to make it quicker for you. But anything we can do with whole numbers, like solving equations, we can do with the fractions in there. Or we can do with decimals in there. Something like this. Here, is there anything we can combine on each side? Nothing to combine on each side, but the variable appears on both sides, so what do we have to do? Get it on just one side. And yes, that's exactly right. We subtract 3.4x. Make that go away. Subtract 3.4x over here, giving us 1.4x minus 3.1 is still there, equals 7.8. Then what? We add 3.1. So 1.4x equals 10.9. And then we divide by 1.4. So x equals 7.79. We can go with that. Technically, that'll go on forever. It's 7.78571428571428. We'll go 7.79. My math lab would tell you what to round that off to, by the way. Since we have run into these repeating decimals a few times, and now that we know how to solve equations, let's take a quick look at how do you convert a repeating decimal into a fraction. Any repeating decimal can be converted into a fraction. Maybe not a pretty one, but it can be converted. Let's take an equation like this. 3x plus 7 equals 34. Now, if we were to solve that equation, we would get x equals 9. I'm going to trust that you guys can solve that equation to verify that. But what I want to do right now is something just a little bit more complicated. We said that we can add, subtract, multiply, or divide both sides of the equation by the same value. So if I were to subtract 9 here, I would have to subtract 9 from the left side as well, correct? But instead of subtracting 9, I can subtract something that has the exact same value. X equals 9. If I subtract an x, what I have here is 2x plus 7. What I have over here is 25. Did I change the value of x in that equation at all? No, I didn't. X is still equal to 9. If I solve that, I'm still going to get x equals 9. So even though this looked funny here, I subtracted x from the left side, I subtracted 9 from the right side. I'm still just subtracting the same value from both sides of the equation. Now that's very important. That's a process that comes up over and over in our processes in algebra, is we subtract the same value from both sides, even though it doesn't look the same. So with that in mind, let's take a look at the repeating decimal, 0.63. We're going to put the bar over it to indicate that repeats over and over again, 0.636363. and so on. And we're going to write the equation x equals 0.63 repeating. Now, since 2 digits repeat, 6 and then 3 here, what I'm going to do is this. I'm going to multiply both sides of this equation by 100. 100 because there's 2 digits that repeat. If there was 1 digit that repeats, I'd multiply by 10. 3 digits that repeat, I would multiply by 1,000. So what this gives me, 101 x times 100 is 100x. Over here, remember, this is really 0.63636363. Multiplying by 100 just moves that decimal point over 2 spots. So what that gives me there is 63.63 repeating. Any questions so far? Okay. Now what I'm going to do is I'm going to subtract something from each side. What I'm going to do is this. I am going to subtract the 0.63 repeating. That's going to cancel out the 0.636363. So it's gone. All that's going to be left on that side, on the right side, is 63. What I'm going to subtract on the left side, however, is x. I can do that because 0.63 repeating is equal to x. So 100x minus x, we think of that as a 1x. 100x minus 1x is 99x. Now to solve for x, what do we have to do? Divide by 99. X equals 63 over 99. Now, of course, both of those numbers, 63 and 99, can be reduced. You might or might not see it. You may divide by 3 first, but both of them can actually be divided by 9. 63 divided by 9 is 7. 9 divided by 9 is 11. X equals 7/11. But x also, we defined x to equal 0.63 repeating. Something called the transitive property in algebra. If two things are equal to the same thing, they must be equal to each other. If x is equal to 7/11 and x is equal to 0.63 repeating, then 7/11 must be equal to 0.63 repeating. Well, since we're having fun, let's do one more example of that. Let's do the value that just popped up on our calculator here. 7.7857142. If this kept going, it would be 857,142, 857,142. What's repeating, it actually starts right here and repeats. Those 6 digits repeat. The 7, this first 7, does not repeat. So I'm going to let x equal 7.7857142 with the 857,142 repeating. Now I don't want to start out with that. I want to start out with only repeating decimals, only repeating digits after the decimal. So to do that, I've got to move that decimal point over 1 spot. To do that, I have to multiply by 10. I have 10x equals 77.857142. Repeating. Any questions so far? Okay. Now we can start to convert the repeating part. How many digits repeat here? 6, which means we have to multiply by something with 6 zeros, 10 to the power of 6. So it's really multiplying by 1 million. So 10x times a million is 10 million x. On the right side, multiplying by a million just moves that decimal point over 6 spots. Those same 6 digits still repeat after the decimal point. Any questions so far? This doesn't look like it's going to be fun, does it? I'll let you know a secret. Even for me, this one's not very fun. We're going to get rid of those repeating digits. By subtracting 10x, but remember 10x was equal to 77.857142. So we have to subtract 77 point those repeating digits. So the repeating digits do cancel out. Here we got 2 minus 7, so it's going to be 3. 12 minus 7 is 5. 3 minus 7, so this is 0. 13 minus 7 is 6. 0, comma, 7, 5, 8, 77. Over here, 10 million x minus 10x. 9,999,990 x. And then we divide. Any questions so far? I realize I picked a horrible example to do here. I apologize. But we can still do it. It's not a huge issue. We divide by the 9,999,990. X equals, this fraction here can be reduced. They both end in a 5, or 0, which tells us both of them can be divided by 5. Which gives us 15,571,413 on top. On bottom, 1,999,000. 998, I believe, on the bottom. When we look at that, it's hard to see if they can be reduced anymore. I assure you they can. One thing I'm seeing is I think they can both be divided by 9. Have you ever seen the shortcut to tell if something can divide by 9? It's similar to the one for 3. You add the digits. 1 plus 5 is 6, plus 5 is 11, plus 7 is 18, plus 1, 19, plus, oops, go back down there, plus 4, 19 plus 4 is 23, plus 1 is 24, plus 3 is 27. Is 27 divisible by 9? Yes, so this whole number, 15,571,413, is divisible by 9. Down here, if we add up those digits, they add up to 45, which is divisible by 9. Actually, sorry, they add up to 54, which is divisible by 9. So both of those can be divided by 9. That would be 1,730,157 over 222,222. If I add up the digits here on bottom, those add up to 12. That's divisible by 3. So it tells me that's divisible by 3 on bottom. That only works with 9 and 3, by the way, adding up the digits. There's other rules for the other numbers, but 9 and 3, if you add up the digits, if they divide by 3, the whole number divides by 3. Divide by 9, the whole number divides by 9. One top, 1730157. That does add up to 24, so that's divisible by 3 as well. If you were to keep going reducing this, I'm going to assume you guys can reduce a fraction. That actually reduces to 7 and, let's keep going. I'm going to screw it up if I'm not careful. So 576, 719 over 74, 074. Here's where it gets tricky to reduce this, but if your fraction calculator, by the way, you should be able to enter that now in your fraction calculator and it will reduce it. Nope, that doesn't work. Nope. This one's going to be a tough one to reduce. I'll leave it there. You guys can reduce it from there if you want to. It does get ugly. I could, of course, take out the 7. Which would leave us with 7 and 58,201 over 74,074. We're going to leave it at that. Like I said, I picked a terrible example. That one was pretty tough mathematically to do. But you can see the process still holds. Even though it's a very ugly fraction to reduce, the process still holds. You get that repeating part by itself, and then you multiply by a power of 10 equivalent to the number of digits. Does anybody have any questions on solving equations? Okay, this process of turning a repeating decimal into a fraction is one that's handy to have, depending on what area you're going into. If you're going into a business degree, business profession, you're going to be dealing with dollars and cents. So you're going to be dealing with the decimal version anyway. Fractions aren't so important. On the engineering side of it, keeping exact numbers in many cases is an important task. Fractions are exact, where a repeating decimal is going to have to be rounded at some point. Those are always rounded. So converting those into decimals can be important in certain professions. So our next step from here. We've talked a little bit about converting words into algebra. So our next step would be to create these equations from words. Now we're going to look first at direct translations, like something like 7 less than 5 times a number is 62. If we're asked to find the number, we would have to write an equation. Now, as we pointed out last week, the is often stands for equals. So something here most likely equals 62. What's going to go on the left side? Perfect, 5x minus 7. If we decode that, 7 less than means we're probably subtracting 7 from something. 5 times the number is 5x. So 5x minus 7 equals 62. We can solve that equation. Add the 7, 5x equals 69, and divide by 5. X equals 13.8. In your notes, I want you to try this one. Three times the sum of a number and 5 is equal to 7 times the number decreased by 1. I always find these are easiest if I can find where in the wording, where in that verbiage the equal sign is. This one is relatively obvious. What 3-word phrase indicates our equal sign? Is equal to. There we go. So now we're going to work on what comes before that first. There's our equal sign. 3 times the sum of a number and 5. How do we express that? Perfect. 3 times the sum means we're going to take 3 multiplying the result of an addition problem. So 3 times the parentheses, and the sum is a number in 5. So x plus 5, n plus 5, whatever. Remember, if you're writing these out in my math lab, check in the problem. It'll tell you what letter it wants you to use for our variable. Now we look at the other side. 7 times a number decreased by 1. How do we express that? Perfect, 7x minus 1. Good. Now we solve the equations. If we're asked to find the number we solve, at this point, I'm going to assume you guys can solve that. We might have the sum of 2 consecutive integers. Remember, integers are just our whole numbers, 1, 2, 3, 4, including their negatives, -1, -2, -3, -4, so on. Consecutive means one after another, like 4, 5, or 9, 10, or -3, -2. Those are consecutive integers. The sum of 2 consecutive integers is 47. Find those integers. Well, here there are 2 of them. There's a smaller one and a larger one. It doesn't really matter which one is which. If I let the smaller one be x, what's the larger one going to be? Well, we got to keep it to one variable. X plus 1 would be the next digit up, right? If the first one is 7, the next one would be 8, x plus 1. So our equation here is x plus 1, that's the sum of 2 consecutive integers, is equals 47. So of course that's 2x plus 1 equals 47. We solve this equation. We're going to subtract 1, 2x equals 46, and divide by 2. X equals 23. But we have to be careful. We haven't necessarily answered the question yet. What I'd ask you to do is find the integers. 23 is the smaller one. We need to find the larger one. X plus 1 or 23 plus 1 is 24. So make sure you answer the question. My math lab might ask for both of them. It might ask for the smaller one. It might ask for the larger one. So make sure you go back and read the question carefully to know which one what it's asking for. Okay, we are down to our last 30 seconds. So just a reminder, if you have not already done it twice, quiz 1 is due tonight at 11:59 p.m. Homework 2A is listed as being due tomorrow. Again, technically it's due next Monday, but I recommend that you have it done before tomorrow so you can ask questions. And we'll pick up from there. Anybody have any questions before we go? Okay, you guys have a great day.